Okay, everyone, video time again. I want to have a little discussion on empirical formulas, and this is a really important topic because we've done this in lab this week, and I want to really make sure everyone has a good handle on what we're talking about. The first thing I want to do is kind of define an empirical formula just because the word sounds a little weird, and I totally get that when things sound weird, it's a border to or a boundary to learning. So here is a technical definition from empirical formulas, and I stole the first part of this from Wikipedia. So this is basically just the simplest positive integer ratio of atoms present in a compound. And a great example is if you took hydrogen peroxide, which its molecular formula is actually H2O2, the empirical formula, the simplest positive ratio is just HO. The process we did in lab to develop the empirical formula of our magnesium oxide compound, technically the formula we developed was an empirical formula, and then we'd have to do a later analysis to find out if it was the actual molecular formula. Okay, so that's the basics on what empirical formulas are, and I want to talk a little bit about theory versus experiment right now. Okay, so from the theory side, we spent a lot of time in class talking about theory. How should atoms behave? And if you took a metal and put it in the presence of oxygen and you heated the daylights out of it, what type of things should happen? What are metals reactive? Is there any way you could look for evidence from the periodic table to determine whether metals are reactive or not? And is oxygen a reactive atom? What indication do you have that oxygen might be reactive? Would you think about, hold on, there we go again. Does oxygen form bonds? Why would oxygen want to form a bond? Is oxygen a stable atom? Oh, oxygen has 6 valence electrons. Oh, magnesium has 2 valence electrons. Oh, okay. And you could think about it from the standpoint of electron configuration. Magnesium is 3s2 and oxygen is 2p4, and it wants to be a full 2p6. Do you remember all this stuff? Okay, so there's a certain rationale for why a chemical reaction might happen in the first place, and if you did this, you could come up with a good explanation from theory how magnesium and oxygen should actually combine with each other. Okay, just from theory alone. Well, we always like to do experiments to verify theories. And if I took a metal like magnesium and put it in the presence of oxygen while I was heating the daylights out of it, making it hot enough that the crucible actually glows, what types of chemical reactions would happen? Now, okay, lost my train of thought. Okay, so I want to do a little example here, and I want to take example from your worksheet. And this is taking 6.25. So let's see if I have my bearings here. And I'm going to click on here. I have 6.25 grams. And this time I'm going to take 6.25 grams of pure iron. And you can get this from steel wool. You could even get this from iron powder. I want to take that much iron, put it in a crucible, heat it really hot under controlled conditions, and allow oxygen in so oxygen can react with iron. Okay, now you know iron, you could look on the periodic table and you know that iron could be a number of different oxidation states. And so let's just do that now. And if you do a little bit of reading on this, you find out that iron can basically exist as a +2, so Fe +2 and Fe +3. Now you know what the +1 and the +2 and +3 mean. This is iron that gives away 2 electrons, iron that gives away 3. Well, if you're going to combine it with oxygen, oops, I made a little mark there. If you're going to combine it with oxygen, and oxygen forms a -2 charge. Don't let me catch you saying oxygen atoms are -2. Oxygen becomes a -2 if it takes 2 electrons. What type of combinations of formulas could you get from this material? If you started with 6.25 grams of iron and you heated it, what type of thing could you get from it? Well, most people are going to look at this and going to say +2, -2. Well, I could probably have iron give 2 electrons to oxygen, and I could form the compound just FeO. or I could have a +3 iron and a -2 iron. We have to work a little bit of magic there, but we would end up with the empirical formula, the simplest version of this formula, Fe3, I'm sorry, yeah, don't listen to me, Fe2O3. So the real question right now is, which form is our iron going to take when it combines with oxygen normally in air? Is it going to form FeO or is it going to form Fe2O3? All right, so in this particular reaction, and I want to switch colors. You guys okay with that? Let's go to blue. Let's say we take our 6.25 grams of iron, and upon heating, we get a black oxide to form. And if you actually, if you know the difference between iron 2 oxide, which is FeO, and iron 3 oxide, there's a big difference in color. So there's a certain indication of the type of material that could form just from the color of it. But let's pretend you don't know that iron 2 oxide is black. Let's say the product we get from this reaction is a black oxide that has a mass of 8.15 grams. And that is the mass of our product. And I'm writing very slow. There it is, product. So that is usually another thing which just amazes the heck out of people, the fact that you can take something, put it in a crucible, heat it, and it gets heavier. No, you didn't do anything wrong. Well, what we want to be able to do now is find out what did the iron react with. And if we're kind of hoping the iron just reacted with the oxygen that's in the air and not the nitrogen, and if that's the case, we have enough information with these two things, the mass of iron and the mass of product, to make a determine of the empirical formula of our material. So I actually want to take those two pieces of material, of information, and put them on another slide. All right, we're back. So we have our 6.25 grams of iron we started with, we heated it, and it got heavier. Not that iron atoms get heavy when you heat them, but we added oxygen. It actually stole some oxygen out of the air. And so another way of looking at this is at least 6.25 grams of this product is iron. This product has the chemical formula FeXOY, and we don't know what the subscripts are. We're trying to find it. So if you do a little bit of subtraction here and take 8.15 minus 6.25, you can find out that the actual amount of oxygen you form here is a mere 1.9 grams of oxygen. Okay? Now, remembering back when you look at a chemical formula, the subscripts you see are actually mole ratios. Mole ratios. And we say they're mole ratios because it's really hard to pull out individual atoms of iron and oxygen. It's a whole lot easier to go to the cabinet and grab a mole of each thing. So I can't just take the two masses that I'm given here, 6.25 and 1.9, and put them in here because they're not mass ratios. They're mole ratios. So the only way to find out the number to put in here is if I actually determine the number of moles of iron and oxygen. So I'm going to kind of simplify this page. Okay, so the real task right now is to basically get 2 moles. If I can find the number of moles of each of these two products, I can find the ratios in my chemical equation. So remember, to turn to moles, we need molar mass. So I'm going to take each of these materials and put it over 1 just for fun, and then divide each of these materials by their molar mass. So I know that 1 mole of iron, and remember, chemists hate using up ink, so they chop the E off of mole. I know that 1 mole of iron is equal to 55.845 grams. And I have to do a little bit of division with that. And that's okay because we have our handy dandy calculator standing by. And that gives me a number of 0.11, wait for it, 19 moles. And that is moles of iron. And that's a not very exciting number, but just kind of just hang with it. So I'm going to do the same thing. I'm going to come down here and I have to find the number of moles of oxygen. And the molar mass of oxygen is so close to 16. It's 15.9 99. It was a very strange 9 that I wrote there. That is grams of oxygen in 1 mole of oxygen. And the similar the process, the math gets me 0.1, wait for it, 1, wait for it, and it's 875, but I'm just going to round that 0.119 moles of oxygen. Now, if you take a look, you're seeing something where these two numbers are kind of close, and we could kind of put these into a chemical equation right now and just use those as the ratios. Fe 0.1119, O 0.119, and everyone looks at this and they're like, I have no idea what you're actually doing there. So what we'd really like to do is normalize this, make it so if I actually wrote down the ratio, my pen is going nuts here. If I had the ratio of iron over oxygen, that ratio right now, you know, is 0.1119 to 0.119. And what we'd really like to have here is a whole number subscript. We're not doing any rounding. We're not using scientific notation. But I'd really like to force that subscript there to be 1. So I guess the question is, if you do a little bit of cross multiplication, what does X become? I really want a chemical formula where this number is 1. And if I do this, if I force the 119 to be 1, then everything looks nicer. So basically, the way to do that is to take both of these numbers and divide both of them by the smallest. So dividing both by 0.1119, 0.1119, this number turns into a 1, and I can put it here. And the oxygen, the number I get for that is not quite 1, but it's really, really close. It's 1.06. And this basically tells us, because this number is not like 1.5 or 1.9, this tells us within the realm of experimental error that we are really close, and we were very confident to know that this ratio is most likely a 1-to-1 ratio of iron to oxygen. So this answer here is our empirical formula. Now, how well does this match our theory? If you go back, wait for it. If you remember from here, we basically calculated from theory, we can have 2 forms of iron oxide, FeO or Fe2O3. And I think if you look at the evidence, the fact that it's a black oxide, not like a reddish oxide, it's a black oxide, and the mole ratio is so close to a 1-to-1, we can pretty much come to the conclusion, even though this is not exactly 1.00, we can come to the conclusion that we found the empirical formula. So this is the process we use. This is the process we used in lab, although we used magnesium and oxygen. And whoops, I totally did not mean to do that. But anyways, give this a shot on some of the practice problems. And I'm going to call this video quits from now. I'll make another smaller video just as an example video. All right, peace.